Let me start. Okay. Today, our topic of discussion is noise in AM systems. Okay. In the last class, we discussed the effect of noise on a DSBSA and SSB systems. Okay. Now, let us continue the effect of noise in other AM systems like AM with the both sidebands and carrier. Okay. But anyway, some student asked me about noise power spectral densities a little bit. So before proceed any further to the next topic, let me noise power spectral densities, which I covered in the last few classes, with some more illustrations. Okay. So now let me show you a slide which is having all the power spectra. Okay. So Abhinav, are you there? Can you,
yes, sir.
Can you see the PPT slide?
Yes, sir, I can.
Okay. So it is a PPT slide. Just it is having.
No, sir, it's,
okay,
I'm getting the whiteboard.
Okay, I'll share one more. Now, can you see?
Yes, sir.
Okay. So you see, in the last class, we were discussing about some nice power spectral densities, isn't it? So if you see the first figure of this slide, it is nice power spectral density at the input of a receiver. That is the front end of the receiver. At the front end of the receiver, the nature of the noise is white. Why white? See, the noise power spectral density is constant, flat for the entire frequency range. Okay, and whose magnitude is equal to eta by 2. Why it is eta by 2 and what it means? Eta means eta is the total noise power spread between 0 and infinite frequency. That's why. But here we are showing the noise power spectral density as a two-sided spectrum. That's why we need to divide it by 2. So eta by 2 is simply the power per unit hertz. Okay. Next, after passing this white noise through bandpass filter, because of the action of this bandpass filter, only a band of frequencies of input noise will pass through this. So at the output of bandpass filter, okay, we'll be having only few frequencies of noise. Okay, that's why it is called band pass noise. Okay, before passing to bandpass filter, the nature of the noise is white. After passing through the bandpass filter, the nature of the noise is bandpass. Okay, and the passband is the same as a passband of the signal, because the bandpass filter is attuned to the center frequency, okay, equal to the carrier frequency of the signal, and the passband bandwidth is equal to the bandwidth of the signal. That's why after passing through the bandpass filter, both the signal and the noise will be having the same passband. Okay. Now let me show the same through some little bit animation. Okay. So this is a white noise passing through the bandpass filter, giving us bandpass noise, isn't it? It's very simple and clear. So it is white noise passing through the bandpass filter, and we'll get a bandpass noise. Okay, isn't it? Okay. Next. And one more important noise power spectral density, that is power spectral density of in-phase component of the noise. Okay, we know the bandpass signal, bandpass noise having in-phase component and a quadrature phase components, NC and a NS of T. Okay, and the respective power spectral densities are simply known as GNC of F and GNS of F. Okay, now how to get this one means it can be understood by understanding how you get a in-phase components and quadrature phase component of the noise, that is NC and NS of T from NI of T. Okay, so how we get it? It is simple. The in-phase component, that is NC of T, is obtained by multiplying the input noise, bandpass noise, Ni of T, by cos and then low pass filtering. The same way, quadrature phase component N S of t is obtained by multiplying bandpass noise Ni of t by sine and following low pass filtering, isn't it? So the same thing is when you do the same thing in frequency domain, you get the respective power spectrum. Okay, so how you get the multiplication in time? You know, multiplication in time is equivalent to shift in frequency, isn't it? So when Ni of t is multiplied by cos, you know, the power spectral density, that is power spectral density of Ni, that is Gn of f, t is shifted in frequency both to the left and to the right and left by an amount of Fc. Okay, so when you shift the same, if you take this one is the noise power spectral density Ni, when it is shifted to right by an amount of Fc, what will happen? You know, this is a portion of the spectrum will reach to the center here, isn't it? Similarly, when it is shifted to the left, the same portion here, this portion will centered at origin, isn't it? And what about when it is shifted here? What about this one? This will be locating at 2Fc. Similarly, when this is shifted to left, you know, and this will be shifting at 2Fc, isn't it? So two portions will be overlapping at the center, and two more portions, one is at 2Fc, another is at minus 2Fc. So these two portions which are locating at plus or minus 2Fc will be removed by low pass filtering, isn't it? So then what is left? Only the portion that is centered at origin. There are two portions of magnitude eta by 2. So when these two are overlapping, they are added, and the total power spectrum is how much? Eta plus eta by 2 plus eta by 2, that is eta, isn't it? So I'll show the same thing through the some animations. Okay, see, like that, when these two are shifted left and right, you know, the portions which are shifted to the center will be overlapping and giving us a magnitude of eta. So this is the power spectral density of in-phase component of input bandpass noise, isn't it? It's very simple. Let me show once again. You see, shifting to the center, they will overlap and giving us in-phase component power spectral density NC GNC of F. Okay, and this is about DSB system. Okay, in DSB system, you know, the bandwidth is 2W, isn't it? Which will range from minus Fc minus W to Fc plus W. Okay. Now let us see about Ssb system. In Ssb system also, input of a receiver, that is the front end of the receiver, the noise is white, and is when this noise when passes through the bandpass filter, you know, it will be filtered, and the output of bandpass filter will be again bandpass noise. But what about the bandwidth now? The bandwidth is different because we are designing the bandpass filter to the bandwidth equal to the signal bandwidth, that is ranging from Fc to Fc plus W. Okay, but in case of DSBSC, what is the difference between the bandpass filters which are used in DSBSC and SSB? Only this pass band. In DSBSC, the bandwidth or pass band of a bandpass filter is Fc minus W to Fc plus W, whereas in SSB it is ranging from Fc to Fc plus W, isn't it? So when the white noise is passing through this bandpass filter, the output will be a bandpass signal as a bandpass noise with a pass band equal to this one only, isn't it? Let me show.
Hello.
This is the white noise. When it is passing through the bandpass filter having the bandwidth W, the output will be a bandpass noise with the bandwidth or pass band equal to that of SSB signal, because SSB signal, here we are assuming the SSB signal is an upper sideband SSB. That's why the frequencies are ranging from Fc to Fc plus W, isn't it? Now, in the same SSB system, how do you find in-phase component? I mean, power spectral density of in-phase component of the noise NC. Okay, the same fashion how you found in case of Ssb system, here also you can find the power spectral density of base component. Okay, how this is the power spectral density of input noise. Okay, which is ranging from Fc to Fc plus W. And power spectral density of in-phase component Nc of F is obtained by shifting this to the left and right. When it is shifted to the left, what will happen? See, this portion will come to the center. Okay, when you are shifting, how much you are going to shift? You have to shift it by an amount of Fc hertz. Okay, when it is shifted to left by an amount of Fc, what will happen? This Fc will coincide to 0. So this band will be ranging from 0 to W, isn't it? And what about this? This will be extending from minus 2Fc W2 to minus 2Fc, isn't it? And what will happen if it is shifted to right? When it's shifted to right, this portion, this portion will be shifted to center so that Fc becomes 0. So this portion will range from minus W to 0. And what about this? This will be locating at locating from plus 2Fc to 2Fc plus W, isn't it? So now the extreme portions of the spectrum can be removed by passing through low pass filter, leaving only the center portions. The center portions are simply one portion is from minus W to 0, another portion is from 0 to W, isn't it? So we'll be getting power spectral density ranging from minus W to plus W with the magnitude equal to eta. Okay, because simply these two are placing side by side, not they are overlapping. That's why the power spectral density after combining these two portions will be same and equal to eta by 2, isn't it? Let me show you the same. You see, shifting to the left and shifting to the right. When these two are shifted to left and right, you'll be getting the central portions like this, and the power spectral density is equal to eta by 2. Is it clear now? So this is about noise power spectral densities of both okay. Now okay, is it clear now? So this is how we can understand about noise power spectral densities of input noise and band pass noise, and also their components, in phase and quarter phase components. Okay. So if you have any doubt, you can raise your hand right now. Otherwise, you can also text me later. Okay. So even after the class hour is over, you can text me. I'll explain the same to you. Okay. Now, can you see who are there? Achari, can you see the whiteboard now?
Yes, sir.
Okay. Now, let me continue our discussion on noise in AM systems. Okay. Noise in AM system. This AM system is nothing but a DSB with full carrier. Okay, this is DSB. Okay, double sideband plus full carrier. Okay. So let us assume somebody. Okay, ma'am. I'll 1 minute. Somebody ask me a question. I will respond to him. I will explain. So let us uh, start with the transmitted signal S of t. Transmitted signal S of t equal to AC 1 plus Ka into m of t into cos 2 pi fct. This is a well-known equation. Okay, we know this equation well, isn't it? AC means the amplitude of the carrier, Ka means amplitude sensitivity, m of t is the message or modulating signal, and this is about the carrier with the frequency fc. Okay, this is about the transmitted signal. The same signal is received at the front end of the receiver also, assuming the channel is distortionless channel, except it is adding noise. Okay, so at the input, the same signal is received along with the noise, which is assumed to be AWG noise. And we know AWG means a noise whose power spectral density equal to white and equal to eta by 2. So therefore, at the input of a receiver, that is the front end of the receiver, the signal is given by x of t, sum of these two, because that's what actually you assumed noise is AWG. AWG means additive white Gaussian. Okay, additive means the noise is simply added to the signal to know its effect. Okay, that's why the sum of these two components S of t and N of t. So this is what we are giving as an input to the receiver. But here the receiver is unlike a DSB-SC or SSB. Here the receiver is AM receiver. Okay, the most prominently used AM receiver is analog detector, isn't it? Now let me show the analog detector. So this is analog detector. Okay, that means the receiver with analog detector. Okay, as usual, receiver will be having a band pass filter at the front end, and the output at the output end there will be a low pass filter. Okay, and instead of product modulator in DSB in SSB, here we'll be having analog detector. We know the functioning of the analog detector, which will produce an output which is proportional to the envelope of given input. Okay, so now let us see. We proceed. Once you know the input is sum of signal and noise, output of the band pass filter is the sum of signal component and band pass noise component. So we can write it as y of t equal to AC 1 plus Ka into m of t into cos 2 pi fct plus band pass noise nc of t cos 2 pi fct minus ns of t sin 2 pi fct. Okay, so this is about signal and this is about band pass noise. Okay, now before to proceed, let us find out here itself the power of the input signal and the power of input noise. Power of input signal is simply as mean square value of the signal component. So SI of t, and we can write this is SI of t. Okay, we can write this is SI. Now this is a S1, SI, and this is Ni. Okay, we know this. So now we can write it as input signal power as SI of t mean square value, which is equal to AC into 1 plus KA into M of t into cos 2 pi FCT, okay, whole square mean. And this can be written, see, once again, you have to remember one important thing, the powers is additive here. Okay, and we can think of this entire term as a sum of two terms. One is a constant term, one is AC into cos 2 pi FCT, another AC into Ka into M of t cos 2 pi FCT. Okay, and we can find out the powers independently, separately, and we can add them, isn't it? What about the power of AC cos 2 pi FC AC square by 2? Similarly, what about the power of AC Ka into M of t cos 2 pi FCT AC square Ka square by divided by 2 and the power of M of t, isn't it? So simply we can write it as S square 1 plus Ka, okay, we can write it as M square of t mean divided by 2, and further in simple form we can write it as S square 1 plus Ka square into P sub M, okay, that means power of the modulating or message signal divided by 2, okay. So you have to remember this, how to get it. You can write it as AC into, right here, it is written as AC into cos 2 pi FCT, okay, and plus AC into Ka into M of t into cos 2 pi FCT. There are two terms. And what about the power of sum of two terms? Simply equal to the sum of powers of those two terms separately. The power of the first term is AC square by 2 because it is AC into cos 2 pi FCT, no? So the power of the first term is AC square by 2. And similarly, the second term is AC square Ka square, because it's a constant. So AC square Ka square divided by 2 into the power of message signal M of t. Okay, so that's what actually written here. So after after substituting for this mean square value of M of t as P sub M, the power of message signal or modulating signal. This is about input signal power. Now, what about input noise power? So input noise power, again, mean square value of input noise. Okay, input noise mean square value. So how do you find mean square value of input noise? What about input noise? Input noise is a band pass noise. Okay, so I'll show you the band pass noise. Here the band pass noise is having the same bandwidth as that of signal. Okay, so this is band pass noise. So for this band pass noise, if you look at the pass band, it is ranging from plus FC minus W to plus FC plus W, isn't it? So, and having the magnitude equal to eta by 2, we can find out, and that too there are two portions. So 2 into integral FC minus W to FC plus W into eta by 2 into df, and it is equal to how much? 2 into eta by 2 into 2w, and it is simply equal to 2 eta W. Now we can write input signal to noise ratio SNR I as the ratio of input signal power to input noise power, which is AC square into 1 plus K square P sub M divided by 2. And after substituting 2 eta W, it becomes 4 eta. So this is about a now proceed. Proceed to find out the output of envelope detector, because this is about the input signal to noise ratio. So we need to find output signal to noise ratio. For that, first we need to detect the signal, isn't it? And what about this envelope detector? This envelope detector is detecting the signal. How it is detecting the signal? By detecting the envelope of the input. Okay, that's why if you write the input in a simple form, then it is easy to find out its envelope. Simple form means you can, if you write the input as a single sinusoid with a variable amplitude and variable frequency, a variable phase, we can easily detect the output. Okay, how that can be done? So for that, we write the input to the analog detector in a convenient form. So what is input to the analog detector? It is equal to signal, that is Si of t plus Ni of t, that is AC plus, sorry, AC into 1 plus Ka into M of t into cos 2 pi FCT plus NC of t cos 2 pi FCT minus ns of t. Now I have to write this as a single sinusoid. So first I am adding these cos terms, AC plus AC into Ka into M of t plus NC of t, okay, into cos 2 pi FCT minus ns of t into sine 2 pi FCT. Is it clear? Now, you see, some function, time function, cos, and some other time function into sine. So we can write this as a single sinusoid with the variable amplitude and variable phase, like E into cos 2 pi FCT plus phi, okay, plus phi, okay, or phi of t, you can write it also because it's a function of t, E and now where E equal to, see how you can write E? E is simply square root of sum of squares of this term and this term. For example, if there is, I'll write here some A cos theta, okay, B sin theta can be simply written as some C or some D. I'll write some D cos theta plus some phi, okay, where d equal to square root of a square plus b square and phi equal to tan inverse of b by A. Okay. Keeping this in mind, you can write it as E equal to square root of sum of squares of A and B. That is AC plus AC KA into M of T plus NC of T whole square plus NS of T square. Okay. And anyway, the angle is material to us. Okay, because the output of an envelope detector is proportional to the envelope of the input signal. Okay, anyway, it is connected to the anyway, it is not connected to the phase of the input signal. So that's why I'm not writing here. And here, if noise is small, okay, if noise is small, what about these two terms? When noise is small means when noise n of t is very small compared to amplitude of the carrier, then we can neglect this term. Okay, we can neglect this term by comparing with this term, because this term is having AC into and so on, and AC is very large compared to the noise component. If n of t is small, automatically ns and nc both are small compared to AC. That's why the second term, that is ns square of t, is small compared to the first term. So we can neglect the second term. Okay, so we can write it as, we can write E as simply this one. So under root and a square of this one. Square root and a square will get cancelled, giving only AC into AC K into M of t plus MC of t, isn't it? So this is the term we get as E. Okay. So this is the envelope of the input signal to the envelope detector. So what about the output of envelope detector? Output of the envelope detector is only the envelope of the input. This is this one. So it is equal to E, that is AC plus AC into KA into M of t plus NC of t. Is it clear? And here this AC terminal is a constant, can be removed by passing through low pass filter as well as a blocking capacitor. So if you pass this through a capacitor, if you pass this envelope E through a capacitor, the capacitor will block the DC, so AC will be removed. And okay, after passing through capacitor, so V naught of t, I'm writing it as a V naught. Okay, V naught of t equal to simply AC into KA into M of t plus NC of t. And now, you see, this is output signal component, and this is output noise component. And as usual, you can find out the output signal power and noise force. Output signal power is simply how much? S naught of t in square, which is equal to, okay, AC square, KA square, M square of t is equal to AC square, KA square equal to PA. Okay, the same fashion you can find out PN naught. So PN naught is simply N naught of t whole square value